Okay. So welcome everyone to the third day of React. So the first lecture today will be given by Uwe Nagel. So this is the course on symmetries. And yeah, it looks like the topic is going to be finiteness up to symmetry. Thank you.
Yeah, that's right. Thanks, Lorenzo. Thanks everyone for joining. Yeah, so in the first two lectures, we considered simplicial complexes on a finite set of vertices, and where Stanley-Wiesner ideals correspond to ideals in polynomial rings and finally many variables. The number of variables equal to the number of vertices. Today we want to shift gears in two steps. So first we want to consider polynomial rings and their ideals in infinitely many variables. And in the second step, we will discuss sequences of ideals in polynomial rings where every element in the ideal in the sequence is an ideal in finitely many variables, but the number of variables will grow along the sequence. So that's the plan. And we'll start with sim-invariant ideals. And of course, I will explain the terms in the heading of the section. But let's start with some notation. So, I mean, I will always use capital K to denote a field. And if I have, and then I denote by K in brackets capital Xn, just a polynomial ring in n variables over K. And to start off, let's recall a classical finiteness results about ideals in these rings, and this is Hilbert's basis theorem. So, and this simply says every ideal I in such a polynomial ring is finitely generated. And that I will abbreviate by f dot g dot. And so what does it mean? We have finitely many polynomials. And that there are finitely many, that's the key of this statement. Polynomials f1 up to, say, fs in the ideal such that, and that's also something I will typically abbreviate, every element in the ideal can be written as a linear combination of these polynomials f1 up to fs with coefficients in the ring. So as a formula, you can write every element as a sum I from, or j, let's use j from 1 to s with of the sum over fj with coefficients rj, and the elements rj's are just polynomials in our ring. And we abbreviate this by simply writing that well, we will say that this ideal I is generated by f1 up to fs. And so these polynomials fj, they provide a generating set, and individually we refer to fj as a generator of the ideal. And this is also, you can also take this as a definition of an ideal in a polynomial ring. You can write the elements as linear combination of finite many other elements. And this finiteness statement has also a more fancy description, namely, it says alternatively that the polynomial ring infinitely many variables is Noetherian, because that's the statement just says the ring satisfies the definition of a Noetherian ring. All right, so if you have finitely many variables, polynomial ring is finitely many variables, we have such a finiteness result. Every ideal has a finite generating set. And as promised, we'll want to now consider rings in infinitely many variables. So let me also use some notation for this. And so I will simply use k brackets capital X n, and then n for the natural numbers. So that's a polynomial ring in variables x1, x2, and so on. Or more formally, variables are xj, j any natural number. And so I start the natural numbers with 1. Just to and in this ring, it's no longer true that every ideal is finally generated. Sort of as a simple example, if you take the ideal, let's say that is generated by x1 squared, x2 squared, and so on, or power squares of the variables. I mean, of course, this is an infinite set that generates the ideal. And in principle, you could ask, well, maybe there's a finite generating set that generates the same ideal, but I leave this to you as an exercise that this is not possible. So this ideal is not finitely generated. So in a sense, this is bad news. We like finiteness. At least I do, because it makes my life much easier. I find it easier to deal with finite sets than with infinite sets. But there is something to notice, namely, yes, this generating set is infinite, but all these generators, x1 squared, x2 squared, x3 squared, they all look alike, right? They, in a sense, and what we want to do, we want to make this a little bit more precise, and then take advantage of this and investigate this more systematically. And the key idea is to use symmetry. So let's denote by sim of n. The symmetric group on n letters. And well, this acts on the polynomial ring in finitely many variables by permutations. permutations of the indices of the variables. So if you take a permutation sigma, it acts on xj. So I write sigma applied to xj simply as sigma dot xj, and that's just the result is another variable, namely the variable with index sigma of j. And that gives us actually more formally a group action on the symmetric group on a polynomial ring. And then we define what's the orbit under this action. So in this sense, in this case, the sim n orbit of a polynomial f, that is simply the set of all polynomials that can be obtained from f by applying any of the permutations in the group. So it's just the set sigma applied to f, where sigma is any element in our symmetric group. Okay. Should pause. Any questions so far? Okay. Well, maybe let's do consider an example. And yeah, let's take polynomial ring in 3 variables, and then as polynomial, simply a monomial x1, x3. And then we want to write down what's the orbit of this polynomial. So we get that maybe I should first of all, how many elements are in the orbit? Does anyone volunteer? I don't know. Did somebody write the answer? You can also write it in the chat. Oh yeah, 3. Very good. Okay, so let me write it down. So we get x1, x3. Nothing has changed. It's just the identity. And then you could transpose 2 and 3, which gives us x1, x2. And if you transpose 1 and 2, we get x2, x3. And in a sense, 3 is maybe a bit less than you would have expected, because, I mean, of course, the symmetric group of 3 elements on 3 letters has 6 elements, but that's, of course, depending on the choice. If we apply the group to the element or polynomial x1 squared, x3, then this orbit contains 6, namely the cardinality of the group, many monomials. All right. Okay, so questions? No? All right, so now.
Yeah, Alessio is asking why.
Alessio is asking why, to what?
Why the second one?
Sorry, I got it, because the square is actually giving you, okay.
Yeah, right, yeah, so, I mean,
you might, okay, sorry.
No, that's why that's good, thank you. yeah, I mean, previously, if we exchanged x1, x3 in the example, if you start with the monomial x1, x3, this doesn't make any change. But of course, if we start with x1 squared and x3 and switch the indices, we get a different monomial. Okay. Then other questions, when we want to do now, what we want to do next is we want to vary the number of variables. So we vary n, and that gives us actually an ascending chain of symmetric groups. So just you can think of the symmetric group of one letter embedded in the symmetric group of two letters, and so on. And I should say a little bit, how do we think of it? Well, if you take the symmetric group on n letters, you can think of it as a permutation on n+1 elements, where we just fix the element n+1. So, and if you say this in more fancy words, we consider this group, the symmetric group of n letters, as the stabilizer of the element n+1 in the symmetric group of n+1 letters. But in reality, this is really the natural thing how you would do this. And now we have such an ascending chain, and so we can form the union of these groups, and that's another group. And that group we will denote by sim. I mean, this, or I would be more careful, I would write sim infinity, and that's really by definition just the union over the groups of finite letters with n variable. And well, this group, it acts on our polynomial ring in infinitely many variables, just as before in the finite situation, we permute variables, namely sigma applied to xj is again simply x of sigma of j. And so we can again think about the orbit. And so, for example, we get that the sim orbit of the element x1 squared, well, we denote it analogously to the earlier case, and it just, well, we just get all the squares of the variables, because that's all the images of one under any permutation. And so if we come back to the first ideal we considered, that means that the ideal generated by x1 squared, x2 squared, and so on, it is not finitely generated in the classical sense, but I said all the generators look alike because all the generators are just the elements of the orbit of the monomial x1 squared. So if we, I want to say this, so we have a finite generating set up to symmetry. More precise, I mean, in this case, the generating set has just one element. It's one orbit. Okay, let me again pause. Any questions so far?
So just to check that I've understood this properly, sim would be every element of sim will fix infinitely many, will only be changing finitely many elements of the natural numbers.
That's exactly right.
Okay.
Yes. Yeah, so that's why I introduced this group. It's not a symmetric group of the integers, or the automorphism group of the integers. I want to change only finitely many numbers.
Okay, thanks.
Sure. All right. So now I want to extend the setup just a little bit. So we have already infinitely many variables, and I want to think of what we have considered as one row of variables, and I want to consider finitely many rows of variables. So, so I will fix a positive integer c, and then let's consider c rows of variables. So, I mean, we index these as we in the matrix, right? x1, 1, x1, 2, x2, 1, x2, 2, and the second index goes, and then we have this row number c is starts with xc1, xc2, and so on. And so that corresponds to we use these variables in a new polynomial ring, and then this polynomial ring I will abbreviate it by k brackets capital X c times n. So the variables have indices I and j. I is in the interval from 1 to c, and j is any positive integer. So I use c for a bracket to denote the interval of numbers 1, 2 up to c. And now our group sim, it also acts on this new polynomial ring by permuting columns. If you have this picture in mind, because we define, if you take a permutation sigma applied to xij, we fix the row index I, but we vary the column index and make it the image of j. One word for notation, we started with the case c equals 1, and I will continue. If c is 1, I will forego with double indices and just write x1, x2 instead of x1, 1, x1, 2 going forward. Okay. So why would you possibly care? And here's one example, at least for those who like determinants. So let's take 3 rows, and let's consider the ideal I generated by all 2 minors of a generic, well, infinite matrix. So let me write 3 times infinity matrix. And now there are a bunch of words which I should explain. So first of all, what means generic? That means it's a matrix where all entries are variables, and well, in this case, it's size 3 by infinity. So we have just variables x1, 1, x1, 2, x and so on, x2, 1, x2, 2, x3, 1, x3, 2, and so on. And I should better. So generic means the entries are distinct variables. And what is a 2 minor? That's a determinant. A minor in general is a determinant of a submatrix, and a 2 minor means we consider a 2 by 2 submatrix. So that's a determinant of a 2 by 2 submatrix. And of course, I mean, that's an infinite matrix where infinitely many 2 by 2 submatrices. So this idea, I mean, at least the way I've given it to you, has an infinite generating set. And in fact, you can show it won't have a finite generating set. Again, consider this as an exercise, but up to symmetry, well, this ideal is generated by, it has a finite generating set up to symmetry, namely it's generated by 3 orbits. And well, and what, I mean, I could, well, I don't know if somebody wants to volunteer which orbits I could, which polynomials I could choose to generate the orbits. Well, yeah. I'm
You
not in
could
the
get,
room,
for
so
example,
that's difficult.
1i x2j minus x2i x2j, and then the same with 1 and 3 and 2 and 3.
Yeah, thanks. Thanks. Yeah, so that's absolutely correct. We can just take we use the minus of the first 2 columns. Nope. Sorry, it was too fast. Because if we use this matrix, the minor of this matrix, we can produce by symmetry the minor of any, we pick any 2 columns and the first 2 rows. Okay. Any questions? Yeah. So then let me throw in a definition. Namely, we want to say what are ideals which respect this the symmetry, and so formally we call these ideals sim-invariant. So an ideal in this polynomial ring with C rows of variables is said to be sim-invariant if the following is true. You take any polynomial in I And then if you apply any element of the symmetric group, we get another element in the ideal I. All right, so applying the group action to an element in the ideal gives another element in the ideal. We don't leave the ideal by applying group elements to it. Now, for an example, well, we discussed already two ideals, and they are both sim-invariant. So the first one was this idea generated by the squares of the variables, and the one we just discussed. And we could say this more generally, namely, any ideal generated by sim orbits is sim-invariant. And so, and at this point, maybe I should throw in an exercise where I actually write out. So let's consider the ideal that is the way I give it to you, generated by infinitely many orbits, namely orbits of the polynomials x1 to the n plus x2 to the n up to xn to the n, where n is at least 4. All right, so these are, well, obviously, I mean, the way it's given, infinitely many elements, but what the exercise is, and this ideal is sim-invariant by the previous remark. And what I asked you to show is if, well, it can be actually generated by finitely many elements, and if the characteristic is not 2, then one orbit suffices, namely the orbit of x1 to the 4th. So in particular, this is actually a monomial ideal. It has a generating set consisting of monomials. And this, I mean, I encourage you to do this with just perhaps playing around a little bit with these symmetries. And so, but the point is, we started with a sim-invariant ideal given by potentially infinitely many orbits, but in fact, it's generated by finitely many orbits, and that's no accident. That's true all the time, because there's a beautiful theorem, and which has been rediscovered more than once. So it was first shown by Cohen in 1987, and then rediscovered in 2 steps. So first, Aschenbrenner and Hiller, they proved this if in 2007, if we have one row of variables, and then Hiller and Sullivan proved the general case again in 2012. And the statement says every sim invariant ideal in our polynomial ring with C rows of variables is generated by finitely many sim orbits. Okay, so, and again, and as I indicated in the title, I think of this as a finiteness result because we have finitely many orbits. And you could view this as an analog of the result we started of Hilbert's basis theorem for polynomial rings in finitely many variables. I think this is a beautiful result, but it actually can generalize further. And in fact, the generalizations are the key to proving the result as stated. And so that's the plan for the rest of today. We want to discuss generalizations and then actually discuss the combinatorial idea, how to prove it eventually. So, but the first step, I mean, I can indicate already, so what's the idea of proof? And this is sort of this is a standard technique. You want to reduce to the case of monomial ideas. And so for those of you who know a little bit what this goes via the theory of Gröbner basis. So what you need is a monomial order, and then you choose in each polynomial the largest monomial, and you get a monomial idea which is called the initial idea. So and so then we'll take this for granted, and then it remains to study monomial ideas. One problem with this reduction is, let me state it as a catchphrase, symmetry does not obey order. Right. And so to give one example, so let's just use C as 1, and let's consider the idea generated by the orbit of the polynomial x1 squared plus x2, x3. So if I write this out explicitly, what are the generators? These are all polynomials of the form xi squared plus xj times xk, where I and j and k are just 3 distinct positive integers. And of course, that ideal has the element x3 squared plus x1, x2 as one of its generators. And now let's use the lexicographic order. But let me declare x1 to be the smallest variable, followed by x2, and so on. And so if I use this order, and then lexicographic, so the phone book order, then in this polynomial, x3 is the largest variable, and therefore this is the largest monomial, x3 cubed. And so if you consider this idea, where we take from each polynomial in I, the largest monomial, let's call it in I. So we choose the initial monomial of any polynomial in I. That ideal will contain x3 squared. And as a consequence, this implies that the initial ideal of I is not sim invariant. And that is bad, right? We started with a sim invariant ideal because it was generated by one orbit. But when we pass to a monomial ideal, we get something which is not sim invariant. And maybe as a hint for the exercise, well, why is this true? The initial ideal contains x3 squared. If this were sim invariant, it would also contain x1 squared in the initial ideal of I. But now x1 is the smallest variable. So this would imply that x1 squared itself had to be in the ideal, and that's not possible. That's not true. And again, that I asked you to fill in the details to complete this exercise. The upshot of this is, so that I wanted to illustrate my slogan, symmetry does not obey order, right? I mean, the symmetry destroys whatever order we put on the monomials to single out what's the largest monomial. And so the way around is we want to replace the symmetric group by an ordered version of it. And I should stop here, ask for questions. Are there some?
I have one.
Yes.
So basically, you're saying that this problem of having an initial ideal that is not sim-invariant, this is not really a feature of the term order that you fixed. There's not going to be a suitable term order. Okay.
Yeah, that's right.
I see.
I claim that, yeah, this will happen all the time.
I see. Thank you.
Okay. Yeah, and that's why, but on the other hand, the idea of passing from an arbitrary ideal to a monomial ideal, which is powerful, we want to utilize it, and therefore we want to replace symmetry by, well, some weaker version of symmetry that respects order. And so I suggest we take a break now, and we'll come back to this after the break. Okay, I resume. Okay, so yeah, just before the break, I made an argument that we should modify our setup to have symmetry, but also preserve order. And the key idea is to replace the symmetric group by what's called the monoid of increasing maps. And so I will abbreviate this by the first letters of increasing. So if I would be more careful, I would include N. But what it is, it's just the set of maps from the integers, no, from the natural numbers to the natural numbers, where sigma is increasing. And this monoid, I mean, it's not a group, and that's why I call it a monoid. I mean, but it has an operation you can compose. There's no inverse. And that also acts on our polynomial ring with C rows of variables. And the action is completely analogous to what we have discussed before. On a variable with index ij, we keep the row index, but we adjust the column index by the image of j under sigma. And then, as before, we denote, if we take a polynomial, we apply any element of the monoid to it. This gives us the orbit of an element, and we define again what is an ink invariant ideal, and that's just completely analogous to what we discussed, so I won't write it down unless there's a question about it. Now, a couple of remarks, and this is actually going back to a question previously, or remark. This monoid of increasing maps is actually not a subset of our group sim, because this was pointed out previously, every element of this group fixes all but finitely many elements, but an increasing map certainly does just the opposite, unless it's the identity. However, if we consider any polynomial f, every polynomial involves only finitely many variables where finitely many indices, and therefore the ink orbit of f will be contained in the sim orbit of f. And what's more is every sim orbit of f is the union of finitely many ink orbits. And again, I encourage you to work this out as an exercise, just to practice these concepts. But as a result of these observations, we see that any sim invariant idea is also ink invariant. So that's good, because we want to eventually say something about sim invariant ideal, but the converse is not true, actually. So we get a and to illustrate this, let's look at a really easy example. If you take the ideal generated by the inc orbit of x1, x5. Right. If you write this out explicitly, what is a generating set in the classical sense? You take all monomials xi, xj, but now we have to obey order, right? In 1 and 5, the distance between 5 and 1 is 4. We have to apply increasing functions, so the distance between the indices could only increase. So what this means is that, well, obviously I is at least 1, and I plus 4 has to be less or equal than j. And as a consequence, this ideal won't contain, or does not contain, the monomial x1, x2, but obviously the sim orbit of x1, x5, the sim orbit does contain x1, x2. So this is an idea which is, this ideal I is inc invariant, but not sim invariant. Expressed differently, the class of inc invariant ideals is strictly bigger than the class of sim invariant ideals. Nevertheless, the analogous result to what I stated earlier, due to Cohn, Aschenbrenner, Hiller, and Sullivan, remains true in the what? That was not. I wanted every inc invariant ideal is generated by finitely many, and again, the finiteness is the key message here, by finitely many inc orbits. All right. Questions? Oh, I see in the chat, increasing doesn't mean weakly increasing, strictly increasing. Sorry.
Yeah, and I have another question.
Yes.
So this inc is not a group anymore, I guess.
It's not. Yes.
So is it a semi-group actions or something? So
Yes.
what kind of action?
Yeah, I mean,
Okay.
yeah, it's a semi-group. You have the composition is the operation, but and it's associative. There's an identity element, but there's no inverse.
I see, thanks.
What would be the identity? Like, isn't the identity map not strictly increasing?
Oh, well, I mean, the identity is sigma of I is I. So if I is less than j, sigma I is, yeah.
Yeah. Sorry. Yeah. Okay.
No, this is why I encourage you to do these exercises. It's just to get familiar. Yeah. All right.
Sorry, Uwe.
Yeah.
For the very last theorem, you're still working in K of x c times n. Right?
Oh, yeah.
Okay.
Yeah, one has to be careful about this. Thank you, Alessio. Okay. And that's not the end of it. So we want to generalize this even further. And this is the time when we actually move on to sequences of ideas. So we want to consider the sequence of ideas, I sub n, and this should be a sequence of let me say at the beginning, vaguely similar ideals. Sorry. Where am I? Similar ideals IN. And now each ideal IN is in the polynomial ring with finitely many variables, right? So, so what? Just well, maybe I should write once more. What are the variables? So we have C rows of variables, and the columns n columns. And I suppress the C. The C will be clear from context. So, and why could you possibly care? I mean, first of all, I find this theoretically appealing, but there's also practical reason. If you think about conducting some experiments and with some unknown quantities, and you conduct, well, if you conduct experiments and you increase the sample size, the number of samples typically corresponds to the number of variables. And you would hope once you have increased the number of samples sufficiently enough, qualitative things don't change too much anymore. What does this mean? How could we describe this algebraically? This is sort of an idea in the background. I encourage you to keep in mind. Okay, so how do we get such sequences of ideal? I mean, we have already seen. Okay. I see in the chat, maybe I should explain strictly increasing I less than J implies sigma of I is less than sigma of J. Let's see. Okay. Namely, so let's consider two ways to get such sequences. And we could start with an infinite setting, namely an ideal in our ring with infinitely many variables. But then we denote by I sub n the ideal where we just cut back to a polynomial ring in finitely many variables. All right, so by definition, what is this ideal I sub n? We take all polynomials in I that involve only variables appearing in the first n columns of variables. And then, again, I encourage you to think this through. If we start with a sim invariant idea, then each ideal IN is actually sim n invariant, and that the theorem I stated, the theorem of Kohn, Aschenbrenner, and so on, ensures that there is some index n0 such that the generators of IN can be obtained from generators of I n sub 0 up to permutations. In other words, you take generators of the ideal with index n0 and apply permutations to it. If you apply all the permutations, you are guaranteed to have gotten a generating set of the ideal IN. And similarly, if the ideal I is invariant, then the generators of each ideal IN in the sequence, let me say, look similar. And again, if I would write this out more carefully, we can get them by applying these increasing maps, but we have to be a little bit careful to end up in the right rings. So to capture this, let's make a definition, namely, let's denote by inc sub m comma n the set of increasing maps with the property that pi of m is less than n. In other words, the map pi maps the interval of the first m integers, natural numbers, into the interval of the first n natural numbers. So as an example, if you take, let's say, inc sub 3 comma 4 and apply it to x1, x3. And then we get, well, this is a set of finitely many monomials now, because, well, maybe I should say this as a hint. What does it mean? If pi is in inc sub 3, 4, pi of 3 is at most 4. But pi is increasing, so that means, for example, pi of 1 can be at most 2. And if you work this out, so if you think this through, then you see that the monomials in this orbit are just x1, x3. That's, of course, applying the identity. You can keep 1 fixed, move 3 to 4, or you can, if you map 1 to 2, you have no other choice. If 1 goes to 2, 2 has to go to 3, and 3 to 4, because you have to produce an increasing map. So the last monomial is x3, sorry, x2, x4. All right, questions? Okay. And with this notation, I can make more precise what type of sequences of ideals I want to consider. And so let's write this out. So a sequence of ideals I sub n, and at least one where I sub n is an ideal in which involves only the first n column, and this is called an ink invariant chain if, so what we want the ideals to be compatible with this ink action. So if you compare two indices, n at least m, and we apply maps from ink m comma n to polynomials in M, the ideal generated by these should be in In. So to write this out, so these are all the elements. Pi is applied to elements in In. And pi is an element in ink comma n. But pi is in this set ink m comma n ensures that the image of pi of im involves only n variables, and so we can require that this is contained in in. And again, assuming this makes only sense if n is at least m. But whenever this is true, we want this to happen. And we call the chain sim invariant if, well, we replace the ink action by the sim action, namely we apply sim permutations on n letters to the ideal im. And so this is sigma of im for sigma any permutation in set n. And the condition is this should be in the ideal im. And again, sorry. Apologize for the back and forth. And again, provided n is at least n. Okay, now what this guarantees is the following. Let's start with the sim invariant case. If you have any sim, sorry, let me say, once we have this definition, we can also see how to construct such chains starting from an ideal infinitely many variables. So if we start with the sim m invariant ideal, which involves the first m columns, that can be used to define a sim invariant chain. In as follows, where we define in is simply 0 if n is less than m. And otherwise, well, we just say we apply permutations on n letters to the polynomials in J. If n is at least m. And of course, this, this definition, I mean, if this construction gives, of course, the definition satisfies the condition here. If you fix m, what you have to show to make prove the statement, if you replace the smaller index by a different smaller index, the result is still true. But that's, well, that's again, I leave to you as an exercise. And similarly, we can produce invariant chains, but now we can start with an arbitrary ideal. Right here, in the first case, we had to start with a symmetric ideal, sim n invariant ideal. But if we can take any ideal, infinitely many variables gives rise to an invariant filtration chain. And this time, well, again, we define in to be 0 if n is less than m. And if n is at least m, we apply inc m comma n to the polynomials in J. Questions? Okay, so then let me give this an exercise. What has this to do with what we started? If in is an inc invariant or if you want sim invariant chain, then the fact that we have these inclusions guarantees us that we can take unions. And so if you take the union of the ideals in the chain, in, this will be an ideal in polynomial ring with infinitely many variables, and this will be inc invariant. Or if you started with a sim invariant chain, then it will be sim invariant. But we cannot always reverse this. We had seen if we start with an inc or sim invariant ideal, we could produce a chain, but not always the other way around. And just as an example, if we take for in the inc invariant chain to the ideal, well, let's start. J is I2, and this is the, well, yeah, I should say, let me use C is 1, x1 to the 5th plus x2 to the fifth x1 squared. And that's an ideal in two variables, x1, x2. And then if you apply the ing action, of course, you get all the squares of the variables, and that's everything. So therefore, in this case, the ideal I, which is the union of these ideals I, is just the ideal we started at the beginning. But if n is at least, 2, then In is the ideal, well, what is it? Maybe I should write the definition. So you start with 2, end up in n, apply this to I2, and then what you get is, well, you get, remember we have increasing maps starting with the interval 2. So you can never map, so x1 squared, the most you can get is xn minus 1 squared. So the image is x1 up squared up to xn minus 1 squared. And then you can also get xn to the fifth. But obviously, this is not equal to the ideal generated by the squares of the first n variables, which is the one we would have gotten by our previous restrict construction, where we cut back the union, the ideal I, to n variables. So we have again, this chain of invariant chains, from this point of view, they really generalize invariant and sim-invariant ideals. Nevertheless, the analogous theorem is still true. Let me write it only for invariant chain. Any invariant chain stabilizes. And so what I mean by this is there is some index n0 such that you can always get the nth ideal in the chain from the ideal with index n0 by applying these increasing maps. And similar for sim-invariant chains. Recall that this gives us in particular finite generation because the ideal In0 is in the polynomial ring of finitely many variables. So it has only finitely many generators. So the generators of In0, the orbits of these give you all the generators, and then suitable elements in the orbit will give you all the generators of In. So this probably generalizes, I mean, this is the most general version of the theorem I started with. Questions?
So,
Okay.
Sorry.
So, yes.
Is this a sort of Noetherianity?
Yes, yeah, you could think of this. Yeah, so you could. I mean, one way to express this would be to well. So the previous result about these ideals in infinitely many variables, you could say, well, the symmetric idea of this polynomial ring is sim-Noetherian or inc-Noetherian. Noetherian up to the action of inc or sim. And this is even more general. Yeah, it is analogous to Noetherianist results. Noetherianist result, yes. And there is a suitable setup where you could really strictly make this a Noetherian result of Noetherian type, but that's a little bit more technical, and I want to. I prefer to keep it at this level if that's okay. But you're right. I mean, it's sort of Noetherianist is what you should think in the background. What this says. This was okay.
Yeah, thanks.
Sure. Okay. So then I promise you, I give you an idea how one proves these results. Actually, or in a sense, just the last theorem. And that is actually combinatorial. So let's talk about well-partial orders. So what do I mean by this? Let me state the definition. So a well-partial order, and that's pretty long, so let's abbreviate this by WPO on a set S with, so first of all, it is a partial order. With the following property for any infinite sequence of elements S1, S2, and so on of elements in S, where is a pair of indices I less than j, satisfying that S of I is less or equal than S of j. So any infinite sequence, you can find a pair of indices where the elements with these indices compare. And in this order, if I is less of j, then S of I is less or equal than S of j. Okay. And well, one example is, of course, if you take the natural numbers, the natural order of natural numbers, that's a well-partial order. As an exercise, let me formulate the following. If we have such a well-partial order on S, then every non-empty subset of S has finitely many minimal elements. And so minimal elements means, well, there's no element in the set which is smaller than the given one. And that follows pretty much right away from the definition. And similarly, if you have two sets, S and T, that both have a well partial order, then, well, of course, one can take the component-wise order and the Cartesian product. Of S times T. And so what I mean by this, if we have two pairs, S comma T and S prime T prime, we say S T is less than S prime T prime if S is less or S prime and T is less than T prime. And then this implies that this is also this or the component-wise order is again a well partial order. Well, why is this relevant for us? Well, let me give a corollary of this exercise. The first is typically referred to, or often referred to as Dickson's lemma, namely the component-wise order on n0, say to the k, is a well partial order for any positive integer k. And so I should say, what I mean by n sub 0, that's just the non-negative integers. So now I want to include 0. Okay, and part B of the corollary, once you have this, and this is really from what I said, I mean, well, what we said in the exercise, you just start with the non-negative integers, that the natural order is a well partial order, you get Dickson's lemma, and in the next step you prove that every monomial ideal in finitely many variables, x1 to xn, is finitely generated. So that's the Hilbert's basis theorem for monomial ideals, as stated in the beginning. And what's the hint? If you have two n-tuples in the natural order on n to the non-negative integers to the nth power, you have this relation between the n-tuples if and only if the monomial with exponents a1 up to an divides the monomial with exponents b1 up to bn. All right, now let's do for finitely many variables. We had seen we want to deal with infinitely many. And that goes as follows. So let's make a definition. Let's assume we have a set S with a partial order. on S. And then we want to define the Hickman order on the set S star. And what is S star? This is the set of finite sequences of elements in S. And this order is defined as follows. So we want to compare two sequences. Let me write these as tuples. So S1 up to SP is in the Hickman order. So I put an index H for the new order. It's less or equal than a sequence S1 prime up to SQ prime if there are indices I1 less than I2 up to less than IP, and I sub P is as most Q, such that each S mod J is less or equal than the element S in the second sequence with index I sub J. So in other words, what it means, I mean, obviously this needs Q has to be at least P, and in this larger subsequence, the sequence with more elements, you have to find a subsequence with P elements where you can compare going forward. The first element in the given smaller sequence has to be less or equal than the first element of the second subsequence, the second, and so on. And this is named after Hickman because this order, because he proved the following result. Namely, if you start with a well-partial order on S, then the Hickman order is a well-partial order on this set of finite sequences of elements in S. Why do we care? Let me conclude with an exercise to make the connection to the previous discussion. Namely, if C is 1, you can think about a monomial with exponents x b1 up to bq is contained in the ink orbit of a monomial with exponents a1 up to ap if and only if the sequence A1 up to AP is less or equal than the sequence B1 up to BP in the Hickman order on N0 star. And once you have this, as in the previous exercise, and you use Dickson's lemma to show that every monomial ideal is finitely generated, you can use this observation to show, and then Hickman's lemma to show that every monomial, invariant monomial ideal in infinitely many variables will be generated by finitely many orbits. And I should stop. Sorry. Any questions?
Sorry, so it's BQ, right? Not BP. I think.
Yes.
Okay. Thanks.
Yeah. Sorry. Thanks. No, thank you for pointing this out.
Okay, so I'll stop the recording now.